Late last year, a comet that did not come from our solar system swung past the sun and started heading back out into deep space. As it left, scientists pointed the most powerful telescope humanity has ever built directly at it, and what came back was something nobody had ever measured before on any object from another star system in the entire history of astronomy. This is the story of Comet 3I Atlas, only the third interstellar object we've ever detected passing through our solar system. And why the chemistry hidden inside it is quietly rewriting what scientists thought they knew about how planets and comets form around stars that aren't our own. I'm Your Name, and this is your channel. If real, unfolding space mysteries are why you're here, subscribe now, because this one's genuinely strange. Let's start with what makes 3I Atlas special in the first place. Almost everything we've ever studied in space, every planet, moon, asteroid, and comet, was born here, in our own solar system, orbiting our sun. But every so often, something slips in from outside. An object that formed around a completely different star, in a completely different planetary system, sometimes billions of years before our own sun even existed, drifting alone through interstellar space for who knows how long, until it happens to pass close enough to us to notice. We've only ever confirmed 3 of these. The first, called Oumuamua, was spotted in 2017, a strange, elongated object that came and went so fast astronomers barely had time to study it before it was gone. The second, Borisov, showed up in 2019 and was recognizably comet-like, giving scientists their first real chance to study the chemistry of something from another star system. And the third is 3I Atlas, discovered in the middle of last year, and immediately flagged as something special. Some early analysis even suggested it might be one of the oldest objects ever observed, potentially having formed before our own solar system existed at all. That alone would make it worth watching. But the real story starts once James Webb got involved. In December of last year, as 3I Atlas was moving away from the sun after its closest pass, astronomers pointed Webb's MIRI instrument at it, a mid-infrared spectrometer capable of breaking down light into incredibly precise wavelength measurements. This is the same basic technique scientists use to identify chemicals on distant planets. Every molecule absorbs and releases light at its own specific signature. Point a sensitive enough instrument at something far away, and you can figure out exactly what it's made of without ever touching it. Webb observed the comet twice, about 205 million miles from the sun, and what it captured was something genuinely unprecedented, the first mid-infrared chemical fingerprint ever obtained from an interstellar object. Nobody had ever gotten a reading this detailed from something that came from outside our solar system before. And buried in that data was the twist. For the first time ever on any interstellar visitor humanity has observed, scientists detected methane gas. Here's why that detail matters more than it might sound like at first. Methane is what scientists call highly volatile. It turns from solid ice into gas very easily at relatively low temperatures. If a comet has methane anywhere near its surface, you'd expect to see it evaporating off almost immediately as the comet warms up near the sun. But that's not what happened here. The methane didn't show up in the earlier readings when 3I Atlas was heading toward the sun. It only appeared afterward, as the comet was heading back out. That timing tells scientists something specific. The methane wasn't sitting near the surface. It was buried deep beneath the comet's outer icy shell, protected, and hidden until heat from the comet's close pass to the sun finally worked its way down far enough to release it. Think about what that actually implies. This is frozen gas that had been sealed away, undisturbed, for however long this comet has been drifting through interstellar space, potentially billions of years, only cracking. Open now, because it happened to pass close enough to a star for the heat to finally punch through. And it wasn't just that methane was there. It was how much of it was there. The ratio of methane to water in this comet is surprisingly high, with very few comparable examples anywhere in our own solar system. On top of that, Webb's observations confirmed something else strange. 3I. Atlas is also unusually rich in carbon dioxide, releasing far more of it relative to water than typical solar system comets do. 2 separate chemical signatures, both unusual, both pointing in the same direction. According to the research team, led by Caltech's Matthew Belyakov and Ian Wong of the Space Telescope Science Institute, these molecular ratios point unmistakably toward a colder, more distant formation environment than anything in our own solar system, meaning this comet almost certainly formed much farther from its home star, in a much colder region, than where most of our own solar system's comets formed around the sun. In other words, 3I Atlas isn't just visiting from another star system. Its chemistry is quietly telling us what the other star system's outer edges were actually like billions of years ago in a region of space we will never be able to visit directly. This is one of the only ways humanity has to study the raw ingredients of a foreign planetary system up close, not through a telescope pointed at a star trillions of miles away, but through an actual physical object that formed there, that we can measure directly, sitting right here in our own solar system for a brief window of time. There's one more piece of this that's worth sitting with. As Webb continued watching the comet head back out into deep space, it noticed the water vapor being released was dropping off steeply, faster than the other gases. That makes sense chemically, since water is more volatile than carbon dioxide, but less volatile than methane in certain conditions. And as the comet moved farther from the sun, the surface cooled quickly enough to slow water loss first. Webb's imaging also showed something visually distinct. Water vapor was spreading out far beyond the comet's icy core, released broadly from grains of ice throughout the surrounding cloud of gas and dust, while the carbon dioxide and methane stayed much more concentrated close to the nucleus itself. Different gases, escaping through different mechanisms, at different rates, all captured in a single set of readings. None of this is speculation or a sensational headline stretched past what the data shows. This is published, peer-reviewed research out of a real observation campaign describing a genuinely new kind of measurement humanity has never been able to make before now. We've only ever had 2 other interstellar objects to study, and neither of them gave us anything close to this level of chemical detail. 3I Atlas is the first one we've been able to study this precisely, and it's already telling us that whatever star system it came from built its comets out of a very different recipe than the one that built ours. So here's what actually matters at the end of all this. Comets in our own solar system act like time capsules, frozen leftovers from the earliest days of our sun's formation, more than 4.5 billion years ago, preserving a chemical snapshot of what that environment was like. 3I Atlas is the same kind of time capsule, except it wasn't built here. It's a frozen record of conditions around a completely different star from a part of the galaxy we will likely never send a spacecraft to in any of our lifetimes. And for a brief window, as it swings through our solar system and heads back out into interstellar space forever, it's the closest thing we have to physically holding a piece of another star system in our hands. We don't know which star 3I Atlas actually formed around. We may never know. It's been drifting through the galaxy for who knows how long before we ever noticed it, and once it leaves, it's gone, continuing on a path that will likely never bring it near any star system. Again, including ours. But for these few months, while it was close enough for our instruments to actually read it, it left behind data that scientists will be studying for years. A direct chemical signature from somewhere out there among the stars that no telescope alone could ever have given us. If you want to see what scientists find as they keep analyzing this data, subscribe and turn on notifications because we'll be covering it. Drop a comment with what you think 3I Atlas's home star system might have looked like. And share this with someone who still thinks nothing new is happening in space exploration, because right now, quietly, we've just gotten our best ever look at chemistry from beyond our own solar system.